This week marked the end of an era for the SpaceX Starship program, as the final launch of the Starship in its current configuration took place. It's hard to imagine a more fitting send-off for the first phase of operations at Starbase, a period defined by ambitious experimentation, innovation, and learning through trial and error. The most exciting part, though, isn't what just happened, it's what comes next. The next chapter promises even bolder designs, more powerful rockets, and a glimpse into the future of human space exploration. But before we look ahead, let's take a detailed look at Flight 11, which was arguably one of the most impressive Starship test flights yet. A near-perfect execution that brought everything together in a way we rarely see. The mission began with a previously flown Super Heavy booster, the same one that carried Starship into orbit during Flight 8 in March 2025. After returning to the Star Factory, the booster underwent a careful refurbishment process. Some of the engines were replaced, while many of the original Raptors from Flight 8, 24 of them, remained on board for Flight 11. This combination of reused and refurbished components is a hallmark of SpaceX's philosophy: maximize reusability while learning from past flights. The engines performed flawlessly. Anyone familiar with Starship launches knows the routine by now: a graceful ascent into a clear evening sky, followed by a hot stage separation and the controlled return of the booster to Earth. But this flight also featured a small experimental twist, a new approach to the booster landing burn designed to test improvements for the upcoming V3 generation of Super Heavy boosters. As with previous launches, this mission did not attempt a tower catch. Instead, the booster was directed to descend over open water. This approach offers the flexibility to experiment without risking damage to expensive ground infrastructure. In past flights, the landing sequence would begin with 13 engines firing and then taper down to 3 engines at the final stages. For Flight 11, the team experimented with a modified sequence: 13 engines initially, then a reduction to 5, and finally 3 engines just at the moment of touchdown. SpaceX described this sequence as a trial run for the V3 booster landing procedure. By using slightly less fuel during the landing burn, more propellant is preserved for the next liftoff, which is critical for improving efficiency and performance. Meanwhile, Starship itself ascended smoothly into a suborbital trajectory around the globe, demonstrating precise control and stability throughout the flight. The main objective for this phase of the mission was simple: keep the vehicle under control and avoid catastrophic failures. Not only did Starship remain stable throughout the coasting phase, but it also showcased the capabilities of its wing flaps, which performed admirably without succumbing to re-entry heat. This is an important demonstration of the craft's aerodynamic reliability, a critical factor for future missions. At roughly T+58 minutes and an altitude of 50 kilometers, Starship executed its first planned dynamic banking maneuver. This was essentially its first attempt to change course in mid-flight. Instead of following a natural straight descent arc, the vehicle maneuvered in a semicircular path, a maneuver that's critical for future controlled landings back at its launch site. For missions returning to Starbase, Starship will need to gradually steer itself along a precise path, from its re-entry trajectory over Mexico toward the Texas coastline. Just before landing, it will execute a final twist to align perfectly with the tower and catch arms. In Flight 11, we saw this process in action around T+1 hour and 5 minutes. The spacecraft rotated approximately 180 degrees before flipping downward and firing its engines for the landing burn. Despite the multiple directional changes, it managed to land near the floating buoy camera, demonstrating remarkable precision. A light splash occurred, followed by the booster tipping over and exploding, a final reminder of the power and risk inherent in these early flights. This marked the last time we'll see a Starship launch look like this. Flight 12 represents the beginning of a completely new chapter. Every element, from the Starship itself to the booster and the launch pad, is being reimagined and upgraded. The next iteration of the Super Heavy booster promises not only increased power, but also a striking new design that reflects the lessons learned from the past. At the base of the new Super Heavy booster, we still find 33 engines, but these are now the Raptor V3. They offer increased thrust from 230 tons up to 280 tons, and a simplified design with significantly fewer exposed parts. Every hose and wire previously visible on the V2 engines has been internalized, making the system easier to build and far more reliable during launch and re-entry. SpaceX has completed testing for the Raptor 3 engines, and production-ready units are rolling off the assembly line. The booster's overall height is slightly taller to accommodate larger fuel tanks needed to feed these new engines. A massive transfer tube allows liquid methane to flow from the top of the booster down to the engine bay, a component nearly the size of a Falcon 9 first stage itself. Essentially, it's a rocket within a rocket, a bold engineering solution for more efficient fuel delivery. At the top, grid fins have been reduced from 4 to 3 and arranged in a T-shaped pattern. This change was necessary to integrate the chopstick pin for the chopstick arms into the fin structure itself. Each remaining grid fin has been enlarged by about 50%, making them stronger and more capable than before. This redesign reflects Elon Musk's philosophy of removing unnecessary parts to simplify systems while maintaining performance. Above the grid fins, the new booster introduces an integrated hot stage connection. Since Flight 2, SpaceX has relied on a hot stage separation using a large adapter to protect the booster's fuel tank and vent exhaust gases. While effective, this interstage adapter weighed roughly 10 metric tons and had to be discarded into the ocean after each flight, a solution that wasn't sustainable long-term. The new design replaces it with a triangle-patterned support structure that provides ample space to safely vent exhaust gas. The dome atop the methane tank has been reinforced with additional steel layers to withstand engine heat during separation. Moving up to the Starship itself, the V3 looks similar externally to V2, but it includes numerous internal upgrades aimed at increasing reliability, efficiency, and performance. The V2 Starships were known for occasional failures, often called rapid unscheduled disassemblies, which provided valuable lessons for engineers. Flight 10, for instance, experienced an engine compartment explosion that destroyed 2 rear control flaps. Learning from this, the team at Starbase redesigned the fuel delivery system completely for V3. In addition to the upgraded fuel system, V3 will use the more reliable Raptor engines. The new Starship Super Heavy is expected to carry 100 to 150 tons of payload to low Earth orbit, rivaling the historic Saturn V moon rocket while being fully reusable, a feat unimaginable during the Apollo era. Speaking of reusability, SpaceX has provided a detailed preview of orbital docking and in-space refueling. The V3 exterior will be fitted with docking adapters opposite the heat shield. 2 ships can connect, one designed for sending fuel, the other for receiving, enabling extended missions farther into space. There will be male and female adapters, or sending and receiving ships, depending on mission requirements. After connecting, fuel can be transferred between ships, allowing the receiving Starship to reach higher or more distant orbits. SpaceX emphasizes that V3 is not the final Starship design, but it is expected to be the first to attempt Moon and Mars landings. Supporting these operations is a completely upgraded launch pad and catch tower, often referred to as Stage 0. Flight 11 is the last launch from Tower 1, which uses the inverted showerhead flame diverter. Tower 2 introduces a more traditional flame trench with a water deluge system taller and stronger than before, designed to withstand repeated launches. The chopstick arms, responsible for catching the booster, are now shorter. Shorter arms are faster, more stable, and better suited to the actual dimensions needed. SpaceX learned from the original Mechazilla setup that overbuilding isn't always better. With refined engineering, the new arms are smarter, faster, and more reliable. All of these improvements set the stage for a thrilling next era of Starship launches. Larger, stronger, and more sophisticated, the next generation of Starship vehicles and infrastructure promises exciting missions, innovative engineering, and a glimpse into the future of human space exploration. The upcoming flights are poised to usher in a new chapter that will redefine reusable rockets and orbital missions, setting the stage for Moon and Mars landings and potentially beyond.